still see some familiar faces. So let's see. Yeah, this first presentation in the row of two, as Terry just explained, is about audio transport and routing, with particular emphasis on NMOS IS-08. So I skipped those slides because you have seen me before. That's me. So again, for those who just joined in, 2110, professional media over IP networks. It's about transporting elementary essence data, and the way it is being designed is just like this. We have an SDI signal, which usually contains video and story data and some audio channels up to 16. An ST2110 sender would now encapsulate the individual essences into individual streams onto the network. So we have video and story and audio streams separated from each other, but synchronized through PTP on the network. They can be received anywhere in the network, and of course, if I want to rebuild the SDI signal, a 2110 receiver could subscribe to the video and story data and audio data streams and can exactly rebuild, recompile the input SDI signal. Well, that would be of no particular use. We could use 2022-6 for that. The benefit comes into game if we look at, let's say, an audio processor, an audio console or whatever, which only needs to receive the audio to do some processing on there, right? With an encapsulated format, it would have to receive the full video and story data and de-embed the audio. With 2110, it can just subscribe to the audio only. So it saves a lot of bandwidth and a lot of work, and it's not costing that much anymore. So it's receiving audio, and basically any device on the network can receive and subscribe to whatever it's actually interested in. And it's not only on the reception side, but also on the generating side. We have a camera that can subscribe and story data and raw video, and any number of audio devices can just supply audio streams to the network. That's the way 2110 works in a production environment. So the document structure, briefly explain again. We have -10 system timing definitions, everything which is required to define the transport and the synchronization is in there. -20 defines the uncompressed video, how that has been transported. 21 is about traffic shaping for this high bandwidth video. We have -30 for the digital linear audio, -31 for the AES 3-bit transparent audio, -40 for the SDI and story data. And if we look to audio only, and that's what this presentation is about, the audio transport, we have the -10 document, the 30 and the 31, which relate to the audio transport. So let's have a quick look at the linear audio transport, the -30 document first. So -10 and -30 are required to transport or to understand how linear audio is transported onto ST2110 environment. Actually, what we can say is everything defined here is the very same thing which has been defined in AES67. So SMTPE deliberately picked up on AES67 and said, okay, that's a nice audio transport standard. We take this as the basis for transport of audio in 2110. So let's have a quick look into AES67 then. That's a standard on high performance audio streaming interoperability, initially published in 2013, and the final update has been, or the last update, it's not the final one I can tell you, the last update has been received in 2018. So it's a very well-maintained standard, and it tries to solve this particular problem. We have different audio applications, they're all based on IP, but they can't talk to each other because they're all using different mechanisms or protocols or payload formats. And well, except for Livewire and Ravenna, who are able to exchange since 2012. But AES67 is a layer on top of this, which defines interoperability requirements, which, if they are adopted by all these individual solutions, enables the native IP interoperability among these different solutions. And actually all of these technologies have adopted the AES67 requirements, and they can exchange now streams based on IP through AES67 formatting. So the way it's done, and not going into details, don't be overwhelmed by this. We have technology components which need to be in place, and they are all nicely defined in AES67. And for any of these components, requirements are defined. So how the synchronization is achieved through PTP, what sampling rates is to be supported, what the transport protocol is, so and so and so on. All these definitions need to be in place to have AES67 working. Now what is not being defined is discovery mechanism. So AES67 is silent on how streams are actually discovered on the network. Well, that's deliberately because it's not really required for interoperability. If you know what's on the network, you can make the connection and you can actually exchange stuff. Luckily enough, there are other standards which jump into this, missing piece like NMOS, ISO4, ISO5, which address this part of the functionality. So back to 2110. We can say everything which is in AES67 is the basis for 2110, right? Not quite. We have some constraints built into 2110 with respect to AES67. Now this is another full presentation going into the details, what the particular constraints are, and since I don't want to do this right now, you can download the white paper on that from the AIMS website. There's a detailed white paper explaining the constraints, differences and commonalities between 2110 and AES67. Baseline is there's a very, very good interoperability between AES67 and 2110, and by now all of the AES67 implementers have added those required constraints so they play nicely in the 2110 environment. Now onwards to the AES3 bit transparent transport. Remember, AES67 is pure linear audio only. It cannot transport AES3 signals, which carry additional metadata information. But SMTPE wanted to have this inside their suite of standards. So they developed the -31 document, which describes the AES3 bit transparent transport. So basically, with -31, you can transport anything which can go onto an AES3 line today. It's not just audio with metadata, any compressed audio format like Dolby E or any even non-audio format can be transported with -31 as long as it's encapsulated in AES3. The way it's done is based on the Ravenna AM824 definition, because we had that in place from the very beginning with Ravenna. Everything AES67 actually defines in terms of synchronization or an RTP transport remains in place, so it's absolutely the same. However, for the payload, we need an additional byte. In addition to the L24 PCM data, we now have a byte transporting the PCUV and the block and frame start data. And of course, we also need a different signalization so that the receiver knows, oh, it's not AES67 anymore, it's AM824. So we have a different signalization in the RTP map information. And then any other SDP parameters are the same. So that basically the simple differences of AES3 or -31 compared to AES67. And guess what? We have an initial application for this. We have a technology demonstration right there on the Ravenna booth where we actually transport linear audio objects in an immersive audio setup with AES67 and have an authoring tool which generates SADM metadata describing the positioning and leveling of these different audio objects, and they are transported across the network with the -31 stream by taking the AES3 output of the authoring tool and converting it into a -31, and then we have the -30 and -31, just the metadata with the -31 on the network, and the renderer can pick it up and execute the rendering according to its own rendering setup or listening situation, and the metadata which is generated by the authoring tool based on the linear audio data objects. So that's a technology demo which is available right around the corner if you're curious. So, but what else is required for a working system? We have transport, we have synchronization in place. What else do we need? Well, establishing connections, right? That is not covered by 2110, neither by AES67, and that's where AMR NMOS comes into game. So AMR is the Advanced Media Workflow Association. It's not quite a standardization organization, unlike AES or SMTPE, but it's an organization of the industry where technical recommendations are actually generated. And NMOS basically is a growing family of specifications which are complementary to what SMT2110 or AES67 are already covering. So it's enhancing the functionality of 2110 and AES67. So the applicable NMOS specification are ISO4, which covers discovery and registration so that systems know what is actually available on the network, what devices are available, what streams are currently configured, what receiving endpoints are available. That's all about discovery and registration. ISO 5 is a specification which touches on connection management, so that makes or that allows receiving endpoints to actually subscribe to available streams through the mechanisms defined with the discovery and registration system. And then we have another specification. You see there are missing two. IS-07 are not covering this particular functionality, but IS-08 is audio channel mapping. So by just connecting a stream, we just don't know what to do with the audio content inside the stream. A stream may have 2 channels, 3 channels, 8 channels, but how do we connect these channels to physical I/Os on a particular device? That's not covered by ISO 5. That is covered by ISO 8. So all these 3 specifications go hand in hand when it comes to making connections. Let me run you through the key elements of NMOS to further understand how 04, 05 and 08 actually work. The key elements of NMOS. The most important key element is identity. So in order to know what's going on the network, the particular resources need to have identities, IDs. So actually, if we have a device, that device has sources and receivers, it can generate flows, it may have a sender, and all these particular resources get unique IDs. A device is hosted by a node that also has an ID, so a node can host more devices apparently. A device can host more sources, more flows, and all these have individual unique IDs. That's the idea of identity. Now, ISO 4 comes into game, the discovery and registration, which ensures that parts of the media systems are known and can actually finally find each other. That's the discovery and registration. Here's our identity model again. That's the identity model, a particular node of a particular node. Now what we need is, well, we have more nodes connected to the network, right? It's not just the one. So all these nodes have IDs of their resources. And then there are controllers. They want to know what's available on the network and they want to finally execute connections, right? So and all these devices need to know what's on the network. So what they do is they submit their resources with the ID to a registry service. That can be a dedicated server, it can be a service running on a network switch, it can even be a decentralized service just like Bonjour, located in all the end devices themselves. The question was, is this identified on MAC addresses? No, it's a mechanism based on universally valid UIDs, so GUIDs. So once all these devices register their resources into the registry, of course the control systems can query the registry and know what's on the network. And all the devices have to report any change. They also have keep alive mechanisms. So once a device is disconnected, it will be removed from the registry, either deliberately or automatically. If the timeout, if it's not paying attention to the timeout, it's a timeout detection and the registry removes it from the system. So at any point in time, any state change, any resource is known, is registered in the registry service and can be queried by any interested instance on the network. That's ISO 4. So now we know what's on the network, right? How do we establish connections? ISO 5 is kicking in. ISO 5 is about making it simple for applications to connect or disconnect flows. So it's a connection management interface specification. So here, to make that an example, we have the nodes again. We have the application logic, a broadcast control system or any instance which is executing something, it's controlling the system. We have the registry again. and we have all the devices advertising their resource into the registry. The application logic can query the registry. Now, through IS-05, which are the red lines, their application logic has an interface provided by the nodes to tell the nodes to create a stream and to tell the other side of the things, a receiver, to subscribe to an existing stream. Well, the stream is just, a resource on the registry. So that has the application has now the power to actually tell the receiver, please subscribe to that particular resource on the registry, which is a stream. And now the receiver is executing the necessary steps to establish the flow. Now with multicast, with audio multicast, we all know this is done through IGMP protocol, right? So what the receiver needs is the SDP information of that particular flow. And that's what actually happens. The application logic is pushing the SDP information into the receiver, and then the receiver is executing on its own to actually establish the connection. Now, it is not limited to IGMP. So the whole IS-05 scheme is made agnostic to the particular stream, formats, and protocols. So it can, also use HTTP connections, whatever. The whole IS-05 scheme is written in a way that it's agnostic to the stream format, content, or to the particular transport protocol. So I can't go into detail on this right now. If you're interested, there's a lot of information which is available publicly on the internet, which you will get a URL at the end of the presentation if you're interested to dive into it. But that's the way how you establish a flow connection between a sender and a receiver through IS-05 interface. Okay, now the challenge is, as within the example, let's assume we have a 6-channel surround stream coming out of a device, and we have 6 speakers, all independent individual nodes on the network who need to receive that surround content, right? So the physical connection is clear. Every speaker is connected to the switch. The sender is connected to the switch. That's the physical, that's the network connection. Now, how do I actually distribute the content to the individual speakers? Well, I could set up 6 unicast streams with individual channels in them, so with mono channels, and pushing them to the individual receivers. So the connection management system could go to all the individual speakers and say, okay, you are receiving the left stream, you are receiving the right stream, you are receiving, and so on, right? So the switch would pass on the unicast streams according to the unicast addresses to the individual devices on the network. That's not very efficient because it's 6 unicast streams on a network, 6 times protocol overhead, whatever, and you have to make 6 times the connections. So what other options do I have? Option 2 is we are sending out a multicast stream from the device with all the 6 channels in it. Now, then I can tell the speakers to subscribe to this multicast stream. So every speaker is receiving the same multicast stream with all the 6 channels in it. Now the challenge apparently is, how does an individual speaker know which of these 6 channels it should play back? It's getting all the 6 channels in one stream, and how does it know that it should subscribe to or it should play back the LFE channel out of that stream? That's the challenge, and that's actually where IS-08 kicks in. That's the audio channel mapping interface specifications, where we can map flow channels to device I/O channels. So how does that look like? We have a device which has some input sources, or maybe not, and has some output I/O points, some sinks. The speaker only has the sinks, apparently. A microphone only would have sources. But since this is a generic model, we have sources and sinks, which are the physical I/O points. And then we have an area, a layer, where IS-08, which is covered by IS-08. So within the IS-08, we have input entities defined, which have a particular channel capacity. And of course, output entities with a particular channel capacity. And the devices actually report those capacities to the registry again, so that a broadcast controller knows what are the particular instances there and what is their capacity. And then there is a map as another instance within IS-08, which would provide patching capability. So the controller, by now knowing, okay, we have a particular input instance with 2 channels, and another one in this example with 2 output channels. I know I have a 2x2 matrix, and I have the means through IS-08 to actually execute patching from the 2 channels on the input side to the 2 channels on the output side. This is all specified through IS-08. So how does that interact with IS-05? What's the whole picture of this? Let's say we have a sending device which has a stereo source and is packing these left and right channel into a sender. So the sender is offering a stream to the registry system, so the broadcast controller knows, okay, that particular device is offering a stream, a stereo stream, two channel stream. Now we have a receiving device, and through the advertisement IS-04 we know there's a receiving point which has the capability of receive 2-channel stream. So it's then executing the flow connection through IS-05 between the sender instance of the device and the receiver instance of the device. So the stream is now flowing utilizing IS-05. Now, in order to execute a particular patch, IS-08 kicks in, where the registry knows, okay, that particular receiving device has this particular patching capabilities, so the 2 input channels, the 2 output channels, and then it can tell the device, okay, from that particular stream, I want you to patch input channel 1 to output channel 1 through means of IS-08. This is all specified in IS-08. That's how 04, 05, and 08 work hand in hand to not just only establish connections, but also patch particular channels to physical I/O points. The channel mapping is all described in a JSON scheme. I skip over that. I'm not explaining code here. If you're interested, you will find all that on the internet. Just as you can see, there are the labels and the number of channels, for example, and so on. And what is more of interest is how this actually is proceeding as a process throughout the logical steps or the sequence of steps which need to be established. So we have a controller, which is the acting client on the network, the broadcast controller. We have the NMOS 05, which is supported by sender and receiver, and then the controller is pushing the transport file, the SDP the transport file information into the sender, which generates the stream and also delivers the corresponding SDP file for that stream into the registry, so the client is able to read that particular SDP from the sender, and then the controller is pushing that information into the receiver. The receiver now has the SDP information and can establish the flow through a means of IGMP. These are the 2 steps which need to be executed for IS-05, and then IS-08 kicks in, where the receiver channel mapping API plays a role. So the controller is getting the information about the channel receiver mapping capabilities, the physical IOs, the input channel IOs, and is then executing the patches on the receiver channel mapping API. So we have established the stream, and in the next step we have executed the patching. And these are 2 individual and independent interface specifications. Using one doesn't necessarily mean I have to use the other one, but of course it's helpful to provide means like this. Here's a more complex example, just as a final slide on this. We have a typical SDI gateway which takes in an SDI input on the left side. It's generating a video flow, that's the green one, which has the raw video data as a 2110 flow. We have 16 audio channels which are de-embedded inside the node and provided as independent, two independent AES67 streams on the network. If you look at what this particular example is being carried in the audio channel, you notice that in channel 15 and 16 we have non-PCM data, which appears to be Dolby E data. So it's routed to a different device, a Dolby E encoder actually, a decoder, and it takes the 2-channel of Dolby E information, runs it through the Dolby E decoder, and sends out the decoded audio channels as independent audio channels in one stream as AES67 or -30 stream, which can be received by another receiving point of that particular, whatever the processing device is. And now I can tell the processing device through patching, through IS-08, it should take the stereo signal, which is in the first two channels, and output it on channel 1 and channel 2, but should not take any of the other subsequent channels for the other immersive sound channels, but should take the Dolby E encoded stuff. Patching that one and then doing further other patches on channel, 9 and 10, which might be a language channel or whatever. And so this was just an example how a system can be built with ISO5 and ISO8 and be very flexible from a generic control surface. If you're curious where all this is can be found in more detail, this is the URL. It's you can go through AMBA TV actually. If you go through amba.tv, you will find a link through the NMOS section, and in the NMOS section you will find a link onwards to the GitHub where all this is nicely explained in further detail. All this is open, no licensing fee, no black boxes. All of this can freely be used, and every manufacturer is actually encouraged to support these open standard specifications. Any questions? Yes. Sorry. So the question is there already any company or any manufacturer who is actually using or supporting these protocols? I can tell you from the PlugFest we have executed in the recent past that yes, there is quite a lot of manufacturers, most of them supporting ISO 4, about the same number is supporting ISO 5, and some of them have picked up on implementing ISO 8. ISO 8 has just been published 2 or 3 months ago, so it takes a while before it's been taken up, but we have seen ISO 8 being executed and tested at the recent JTNM PlugFest already. So yes, I expect that more are taking up on this. Any more questions? If not, you got back 5 minutes, minus the 1 minute overtime from my last presentations. There's 4 more minutes of your life saved. You're invited to stay for the next presentation, which is actually